Lecture 10, Causal Inference. There are 9 parts to this lecture. As usual, I will outline the learning outcomes at the start. This lecture is all about causality and the difference between causality and association. And in parts 2, 3 and 4 of the lecture, I'm going to outline the fundamental statistical concepts that we use to understand causality. So that's the distinction between association and causation, the problem of confounding, which essentially separates causality from association, and the principle of identification. Having done that, in part 5 of the lecture, I'm going to outline the basic mathematical framework that we use to derive causal inference. This is a framework that will let us achieve what's known as causal identification. And then parts 6, 7 and 8 will cover methods that can be used to derive causal estimates from statistical models, and we'll talk about outcome regression, propensity scores and instrumental variables. And then finally, I will summarise what we've learned. So, in terms of learning outcomes, at the end of this lecture, you should be able to distinguish the concept of causality from association in the context of a statistical model. I want you to be able to use formal statistical language and notation to explain the concept of identification. This is an important underlying principle that we haven't discussed much so far, distinct from estimation. I want you to be able to identify the properties of data, observational data, that undermine our ability to draw causal conclusions. That is, to make cause-effect inference from data. I want you to be able to explain the problem of confounding and derive its consequences analytically. I'm going to introduce a graphical representation of causality known as a directed acyclic graph. I want you to be able to draw these graphs for different data generating processes with different structures of confounding. We'll then look at solutions for causal identification. I want you to be able to derive them mathematically using the causal inference concepts of potential outcomes and conditional independence. As I said, there's going to be 3 methods that I want you to be able to understand and implement. That is outcome regression, which you already know about, propensity scores and instrumental variables. And I want you to be able to understand and identify the assumptions of each causal method and distinguish settings in which these different methods are appropriate. So let me just provide an introductory slide to say, what is causal inference all about? Well, in this lecture, we're going to consider approaches that can be used to identify cause-effect relationships from observational data, from observed data, without resorting to experimentation. Now, what that means is that we can't control the process that generated the data. We just passively observe the data we get, we collect it, it falls into our models, and we want to attempt in causal inference to determine from the data what causes what. So the main focus in causal inference, as the name suggests, is on inference. It's not in prediction. So in this lecture, we're not really interested in fitted values y hat. We're very much interested in fitted parameters y beta. We're interested in identifying these parameters. We're going to use that word identification. So if we think about something like the best linear predictor of y given x, which we've talked about in previous lectures, this minimizes mean squared error or some other relevant estimation target, and that's good. It provides a good prediction of y given covariates x. But while a model might be BLP in some particular class of models, that doesn't mean that its parameters can be given a causal interpretation. In fact, a model that provides good prediction could at the same time provide bad inference, in the sense that the prediction it gives us of how y will change for a change in x, ceteris paribus, isn't reliable. It's not actually reflecting the causal link between these variables in the real world. So, the application of mathematical algorithms for estimation solves some optimization problem. It could be least squares, it could be MLE, but it doesn't necessarily generate inference that accurately captures complex causal relationships embedded in the data. And just because the R-squared's good, or the t-value, or because the log likelihood's good, or the likelihood ratio, that doesn't mean that the parameters have a causal interpretation. So in causal inference, our aim is not just to achieve optimality in estimation, but to ensure that the parameters we estimate are uniquely identified, such that, other things being equal, they capture causal rather than associational effects, and I'll distinguish what that means at the first part of the lecture. And actually, in a typical causal inference problem, the focus is on estimating the causal effect of a single variable, sometimes just a single parameter. And that variable is known as the treatment, and we're interested in how the treatment affects some outcome of interest. So in a sense, we're narrowing down the scope of our modelling. And we're not interested in a big long vector of betas necessarily. We're really focusing the inference problem on a small number of parameters and trying to determine if those parameters can be interpreted in a cause-effect fashion.